Good morning, everyone. So today let's continue our discussion on Biot-Savart. So Biot-Savart is by looking at little chunks of currents and use integration to find the magnetic field. We have done one example with a long current carrying wire. And now let's look at another example of a current ring. You want to find the B field on the center axis. So let's draw our diagram. This is the current, and we can set our X in here and we set our Z in here. We want to find what is the B field at the center at a Z distance above the center of the ring. Okay, and the radius of the ring is A, which is given, current is given, so we want to be able to find the B field. All right, so due to looking at the Biot-Savart, this is the expression, how you find the B giving a current distribution. Okay, so we want to find out, okay, so how do we simplify the dl cross r hat over r squared, okay, by giving this particular diagram. So, all right. So let's go ahead and have you have a discussion for a couple minutes and we will bring you back. And make sure you take a screenshot. You do need a diagram for this one. You'll be able to look at the geometry and figure out what these quantities are. Okay. All right, let's go for 10 more seconds. All right, I'm gonna go ahead and close this. Let's take a look. It seems like we all agree on what the magnitude of curly R is, right? And maybe the one that's a little bit more confusing is how do we figure out this cross product? Okay, so to look at what R is, actually let's draw a, we could use this diagram, or we can draw a new diagram showing the cross section of the R instead of this perspective view. If we use this particular diagram, and you can see this vector from the source to the field of interest, the red arrow is the curly R, right? Okay, and in the triangle of the red arrow, green arrow, and the blue arrow, each of them represent one of these. This one represents R, this is R prime, and you can see that the angle between R and R prime is 90 degrees, right? So to find curly R, that's pretty straightforward, is going to be, in this triangle, is going to be the square root of z squared, square root of z squared plus, and the radius is a squared. So, so R squared is going to be z squared plus a squared. Okay, so the denominator is going to be either C or D. Right, now we have to figure out what's the numerator. What is a DL cross R? DL cross R. R is a unit vector, so the magnitude of R becomes 1. Becomes DL magnitude times magnitude of R is 1. And then we need to look at the angle between DL and R. What is the angle between DL and R?
Sine theta.
Yes, the angle, the sign of that angle. And what is that angle?
Phi.
So can you convince us why it is phi? How can we convince ourselves it is phi? So let me label DL more explicitly on this diagram. So DL is the source. For this particular source we're looking at is right here. This little section, that's DL, right? So DL and R seems to be this angle we're looking at. This angle. Phi seems to indicate, okay, it's an angle between, okay, if you label this as your x-axis, seems to be, okay, indicating the location of the source. You have many locations of the source. At this particular location, the source is at the angle phi. So are these two angles the same? Let me try to show this using a little ring. So this is our current carrying wire, that's the ring. And you can see that your DL is around this, right? And if I'm looking at this particular DL right here, if I put it right here, right now, this DL is facing into the page, into you guys. Do you agree? If my current is going counterclockwise, and at this particular point, the DL is pointing inward into the page of the screen. Do you agree? Right here. Yeah, go ahead. So DL right here is into the page, right? It's coming towards you guys.
Right.
So that's your DL. And that is which is my R. R is from here to the center. So this is going to be my R. So this is going to be my R. From I have to deform the range just to be able to hold it. But remember, this is your DL into the page. And this pencil is now representing the R. So I want you to look at this again and tell me what is the angle. Maybe it's a bit harder because can you guys look at this and tell me what the angle is?
Someone in the chat said 90.
Okay. Yeah, 90 degrees. Very good. you notice that if you look at the cross section right here, DL is into the page and R is actually a line in this page. So if you're perpendicular to the page, you're perpendicular to any vector that's on the plane. So it will be a little bit more clear if I draw the sort of the cross section of the view. So let's say we're gonna look into the page right here, right? Your eyes, let's say your eyes is here. You're looking into the page. So you will see this image. You will see, okay, I see a Z, okay? And I'm seeing here at a radius A, you have a current going into the page. So you're gonna draw your current into the page as DL, like this, right? And what is your R? R is from here to here, and this is your R, right? So you can see DL is into the page is perpendicular to R, okay? DL is perpendicular to R, okay? All right, so because DL is perpendicular to R, when you do cross product between DL and R hat, you simply just going to be DL because sine 90 degrees is 1, right? So going back to this, it turned out we should choose D as the correct answer. Okay, so now let's go ahead and do the cross product, see in which way is the B field, the DB is going to be pointed at. Okay, so this is your DL into the page. I'm looking at my page right now, or if I'm facing you guys, is like this is your DL. And R is, so this is my R. So I need to swing across my four fingers toward where my R is. So you can see the thumb is pointing in my B direction. So this is my B. You see, this is DL cross L. Okay. So, and this is going to be the direction of DB here. Now, of course, if you look at an DL on the other side, out of the page right now, you're going to have a DB over here. And you can add all of these components, the one component that you need to find the B field. Okay, so now you probably have already figured out which is the component that you need to do the integration, right? So that's the next question, which is the Z component. You want the Z component, that is the B field, because all the other components cancel due to the symmetry, leaving the B field is pointing out of the page, pointing upward at the center of the ring. Okay, so how do we find the Z component? You can take a screenshot of this page. I may want to refer, I'm actually going to add my diagram here so you can refer to it here. Okay, so this is your DL, this is your R, and this is your DB, okay? And we want the DB in the Z direction. Let's call this alpha, and this is 90 degrees minus alpha, right? Because this is 90 degrees, so this is 90 degrees minus alpha, and this is alpha, okay? So this is A, and this is Z. All right, so I'll let you go ahead and discuss for this for a couple minutes. All right, any last minute vote? Just 5 more seconds since I gathered a majority of vote already. 5 more seconds. Okay, so now let's take a look. We want to find the z component of the B field. Okay, very good. I think this is the cosine. You want the cosine of this B field, right? All right, so let's see in the diagram. It's easier to see that from this cross section of the diagram that the BZ is what you need, which is dP times cosine alpha. And let's see how it can we represent cosine alpha of the other quantities. So we need BZ is the integration of dB and the Z component. That is going to be dB times cosine of alpha. And what is cosine alpha? You can see this is alpha, and that is 90 degrees minus alpha, which means this angle is alpha, right? So cosine of alpha is going to be the adjacent, which is A, over the hypotenuse, which is R. So that is square root of A squared plus Z squared. So putting everything together, BZ is going to be mu naught I 4 pi the DL cross R over R squared, you already reduced to DL over A squared plus B squared, remember? But also we need the cosine alpha, which is this one. Okay. So you can see that it actually becomes very easy to integrate because you are really just integrating the sum of all the DLs, all the length. Okay. And that is simply going to be the circumference of this current ring, which is 2 pi A. Okay, so my B field at the center, I have found it to be mu naught I. I'm going to cancel the A here and the 2 pi here, leaving the 2 here over 2. I'm sorry, A did not cancel. A becomes A squared over A squared plus V squared over 3 halves. Okay, so that is a B at the center as a function of Z. Okay, B at location 0, 0, Z is equal to this quantity. All right, so you can see correct answer actually is A. We need the cosine, it's not the Z. Z is the sine alpha, and we want the Z component, which is the cosine alpha. Okay, so it's going to be this guy. Let's sum up. We have found to find the B field using Biot-Savart, mu naught I dl cross R hat over R squared. That's for a line current. Sometimes current, if it's not just a line current, we have two other equations. So you can see if it's a surface current. Okay, then Biot-Savart becomes B is equal to mu naught over 4 pi, the integral of K cross R hat dA over R squared. If it's volume current density, then B is going to be mu naught 4 pi integration of J cross R d tau over R squared. Okay, so if you have a wire, you use this. If you have a surface of current, you use this. This is if you have a current flowing through filled within a volume, then you use this equation, right? This is very similar to we have calculated the B field, the E field, right? Using this density or this density or this density, right? You will choose whichever equation you use given the situation. We also did the current carrying wire, the B field due to one of the wire. If you have a current, it's going to be mu naught I over 2 pi S. So if you have two wires, this is something you probably find very familiar with current I1 and I2. So there's going to be force between these currents, right? So it's actually different from in E field, you have a positive and non-positive charge, they will actually repel each other, right? If you have a positive and negative charge, they will actually attract each other. But here, if you have the current flowing in the same direction, like current actually attract. So this is actually different from what we remember from electrostatics, because there is a B field as being produced by one of the current. Let's say you have the B field right here, produced by I1 is in what direction? Use your right hand rule. You see that is actually in the direction of into the page. There is a B field due to I1. So I2 will feel a force. So F is on I2 by B1 is going to be, this is the equation we derived before. So I2 DL2 cross this B field. Okay, so B is into the page, current DL is up. So use your right hand rule into the page and oh, wait a minute. Yes, it's so current is going upward and B is into the page. Use your right hand rule. You get the force is pointing to the left. So this is your force, right? Pointing to the left. So if I call this the X direction and this is the Y direction and this is the Z direction, the force is in the negative X direction. It's going to be mu naught I2 times I1 over 2 pi S integration of DL2 in the negative X direction, negative X hat direction. So if you look at this I2, the force by unit length, so you can get rid of the DL. So this force will change depending on how long of the current you give it. So instead of looking at the total force, we say, what is the force per unit length? That's just going to be mu naught I1, I2 over 2 pi S. That is toward I1. So you can see the force between these two currents are actually toward each other. So they attract. If you have two currents flowing in opposite directions, then they will repel each other. So like currents attract and opposite currents repel. Okay. All right, so we have done two examples actually. One is a wire, long wire. One is a rain using this equation. Now let's actually look at an example using this equation to do a surface current, okay? Right. So here we have a surface current that is flowing in the X direction and is living on the XY plane. Here it already gave you what K cross R will reduce to. Okay, but we can set it up and kind of start over a little bit before we jump to the conclusions. Okay, so let's look at this example of the surface current. We have a sheet of current with a current density K. It's in the X direction. Let's see if my diagram is going to be. Okay. So during the Biot-Savart, B is going to be mu naught over 4 pi K cross R over R squared dA. And let's see if how can we reduce this to the result that is given to us. Okay. Okay, first of all, it replaced R hat with R vector. So we can do that. So R vector is going to be, R hat is going to be R vector over R. So this becomes R cubed dA prime. So to do K cross R, you need to know what K is, represent what K is, and need to know how to represent R. Okay, so let's look at this diagram. Your K is on the XY plane. So how do you represent the location of any if I'm just choosing a random location right here, how do I represent the coordinates of this location, of this source? It's on the XY plane, so the Z is 0, and it has some random X and Y, right? So I'm going to say X prime, Y prime, and 0. So I'm going to use X prime, Y prime 0 to represent the square dot of R prime. Okay. So I'm going to draw a little bit source right here. The location of the source is going to be R prime. Okay, so I'm going to claim that R prime can be represented using X prime, Y prime 0, because it is simply a random point on the XY plane. And it's also the source, that's why you have the prime. And this is the field, right? Here we're trying to evaluate the B field above the surface. So how I'm going to write, and this is going to be my R vector. So how do I write my R vector? So R prime is at X prime, Y prime 0, and R is at 0, 0, Z, right? So now you can write your vector R going to be R minus R prime. So R minus R prime. So let's do this. It's going to be negative X prime, negative Y prime, and Z. So I found my curly R, okay? So in this cross product, I found the curly R. Next, I need to write K. So K is flowing in the X direction. So how do you represent K? So how do I represent K? Some constant in the X direction. So it's just that, like that, right? Or you can write it using K, 0, 0. Okay. So so far so good before we plugged it into the cross product. So anybody have any question regarding how we got R and K? All good? Okay. All right. So if that's all good, we can just simply calculate the K cross R. Going to be X hat, Y hat, Z hat, and K only has the X component, and R is negative A X prime, negative Y prime, Z. So plugging into this matrix, you get K cross R become negative KZ Y hat minus KY prime Z hat, okay? So if I plug this back into this equation, I've got this, okay? Okay, let me just write it one more step. So B is mu naught over 4 pi. K cross R has become this, and I'm going to put the negative sign in front of everything, negative, okay? K, we have a common K, so I'm gonna put a K in front of everything, okay? It becomes Z, Y hat, plus Y prime, Z hat. And the area, this is the area of the XY plane. So it's going to be dx prime dy prime, that's dA, over R cubed. And what is R? R is right here, so you can find your R from here, right? So R cubed going to be this entire thing to the power of 1/2 cubed, so we get 3 halves. So that's why we have this equation, okay? So this is a B at 0, 0, Z. Not everywhere, only at 0, 0, Z. The above equation. Okay, so this is how everything is set up. Once it's set up, we can further try to calculate the B field. You can do a symmetry argument. I would say you have two choices here. You can reduce B simply. I'll tell you further by looking at you can either look at the symmetry, you do right-hand rule, you can look at the symmetry, or you can look at this expression mathematically to see which of these integration actually will go to 0 and which integration survives. Okay, so I'm going to let you go ahead and take a screenshot of this picture and have a discussion on, so let's do this calculation. What is the component of the B at that location? Will you end up with only one component or you have both components? It doesn't look like it's going to have an X component though, because here we only have a Y hat, Z hat. Okay, so you have the two options, either looking at symmetry, doing the right-hand rule, or you can look at the math. All right, so I'll let you go ahead and have a discussion. All right, so 10 more seconds. Let's do 10 more seconds. Okay, any last minute vote? Okay, so now let's take a look at our results. So kind of all very split between either one of those two, Y or Z, or maybe both. And this all looks awfully complicated. Do we actually have to go ahead and enter this lower and upper limits and actually do the calculation? Is that the approach that you take? Or do we enter using this and put it into Mathematica? So is there an easy way that we can quickly tell? Anybody would like to share their thoughts with us? I would like to curious to see what you think.
I was thinking that the Y component is constant,
Okay.
if K is constant. And then since just the Z component would change, I guess I thought it would cancel out.
So you're saying the B field has which component only?
Just the Y component.
The Y component, and Z component cancels. So how do you know that?
Let me see. So the Y component, it only has a dependence on Z.
Okay.
Oh, maybe not actually. I didn't look at the denominator. So
You can draw two overlapping circles and put like a arrow showing the direction of the B field, and then see the components cancel.
Okay. So I've heard two different methods to do this. Very good. Brendan said we can looking at symmetry using the right hand rule, looking at the current going a contribution here with a right hand rule circle and another current going here and see how they cancel. And Matthew said he looked at actually the function. I would say that's very good. Both methods will work here. So let's look at the first method together. So let's see, we wanted to evaluate this using mathematics, realizing what we have to integrate the Z component and the Y component separately. So what is this integration we're doing? For the Y component, we are integrating dx and dy prime. These are my integration variables. So each of them are from negative infinity to positive infinity, right? You agree? Because this is how your source extends from negative infinity to positive infinity, have a large sheet, right? So what you're integrating in the Y component is Z. Yes, Z is, you can treat it as a constant. So if this is too confusing, you can temporarily set Z to some variable A, and then do your integration and replace the A back so that you don't get distracted. But Z is really just a constant here. You are integrating this function, right? So you're really integrating this dx prime dy prime. The Z component, everything else is the same, and it has a y prime, okay? It's here, dx prime dy prime, x prime squared plus y prime squared plus z prime squared. So we claim that just by looking at the mathematics, we can claim this component goes to 0, leaving only the y component. So I wanted to remind you of some simpler integration that you already know. So for example, if I ask you, what is y dy from negative infinity to infinity? What would you tell me?
I would say it's 0 since it's an odd function.
It's an odd function, yeah. But if I give you y squared, actually, I don't want to use this. Mathematicians probably don't like how we do this, but let me just do a -5 to +5. So an odd function, you integrate it, you actually get a even function, so that the lower limit and upper limit give you the same number because you get a square, right? But if you do a y squared, you get 1/3 y cubed. Now this is 0, but this is not 0. So this, all of this applies to all the odd functions. Y cubed is going to be 0 as long as your integration limits are symmetric and all the even functions are not 0. Do you agree with that? So because of that, we know, oh, let me observe this integration. This is y prime square. So this is denominator is a even function, but you have a y prime here that make it overall odd, so that then you do the integration, you don't even need to do it. You know it's going to be 0, right? And the x doesn't matter. As long as y is 0, everything is 0. But this one is not. This one is not going to be 0. So by that observation from math, you know that, okay, I actually will have my y component, z component cancels. So now let's look at the symmetry argument, the different method. If we were to draw, so you have all the surface current. So I'm going to select simply one line by looking at the current as many lines. If I look at, okay, let's say one of the lines going this way. And if I do right-hand rule, I'm going to have a circle sort of surrounding this line. On top of the line, my current is going to the left. Okay, here, right here, my current is going down, right at the edge. That's going down, and I'm going to look at a symmetrical line that's located on the other side. Right, so this is another line. I'm going to draw another circle for this line. You can see that, okay, I'm drawing another circle. So here on the top is pointing to the left, okay? Here, over here is actually pointing upward. So you can see that these two symmetric current contributions have the z component cancels out. One is, so this circle this way, this circle this way, one down, one up, so they cancel out. But the y component survives, right? The y component going to the left and going to the left, they actually double up. So this one survives. So this one, you can even tell the direction of the B field is going to be in the negative y direction, as also indicated here in the negative y direction above the plane. You probably already noticed below the plane is in the negative y direction. So this is your surface coming towards you in the x direction. Above the plane, your current B field is to the left. Below the plane, your B field is to the right. Okay, it's kind of like the electrical field for a surface, very large surface of surface charge density. Right above the plane is up and below the plane is down. It's kind of like that. I don't know if that analogy helped. So there are two different ways you can figure out which component cancel, which component survives. Later on, and you can see this is very labor intensive. To do Biot-Savart for a surface current density is very labor intensive. Luckily, we have a very simple method. That is the Ampere's law. We can solve a lot of magnetic field problems if you have the right symmetry. So this is our next topic. Is Ampere's law. We can, the status of Ampere's law is just like Gauss's law in electrostatics. So the status of Biot-Savart is like Coulomb's law doing direct integration. But when symmetry applies, we have a simpler method that's using Ampere's law. So a surface current like this, you can simply use Ampere's law to solve it. And we will work it out a little bit later. Okay, all right, so let me write up what we need to do. Ampere's law is telling us what the source of the magnetic field, just like the source for the electric field is given by Gauss's law. So here we have the curl of B is equal to mu naught J, right? And of course, there are two other laws, that is the divergence of B is 0 And later on, we will do the curl of E. In electrostatics, it's always 0, but in time-dependent situation is not. But that one, we are not there yet. It's going to be dB dt, but that's for later. For now, it's really simple. All we concerned is 0. Okay, so this is Ampere's law. This is the differential format of the Ampere's law. Okay, so from Biot-Savart, you can derive Ampere's law, and from Ampere's law, you can show Biot-Savart. You can go back and forth between two laws. All right. So what we want to do is we want to be able to, like, remember we had this practice in our very first chapter. We said, okay, from the differential expression of Gauss's law, you can derive the integral expression of Gauss's law, Q enclosed over epsilon naught. Okay. So right now, I want you guys to be able to derive the integral format of Ampere's law using the differential form. So what comes to mind? What do we do? So first of all, can you guys tell me what is the integral format of Ampere's law? What does that look like? The integral of something equals something.
EDL.
EDL, very good, is equal to
Mu naught I enclosed.
mu naught I. Yeah, very good. So from here to here, how do we go from here to here?
Maybe the curl theorem?
Yeah, we know that. Stokes theorem, right? Saying that the curl of any vector, if I look at the surface integral of that vector is equal to the line integral of that vector over a closed loop. And the surface is described and defined by this closed loop. Okay, so continue to think how you're going to do the Stokes theorem. I'm going to import my other file. Okay. Okay, so here we just treat I as the scalar. We always put our vector sign onto DLs. We use Stokes theorem. And as we say that this dA is actually defined by the DL. Okay, so as we go through this, we will eventually derive it. So, but you realize there are more than one way to define and find this DL. So think about that so you probably have experience of making bubbles, right? Soap bubbles. So if you take a line, this is a closed line. Imagine this is a metal wire. And if I put this in my bubble mix, and of course, I'd be able to make some bubbles. If you gently blow on it, sometimes your bubbles will even go on this way, right? Like the shape looks like this. Or you may just have the bubble mix within this line. So you can see there are more different ways to define a surface using a closed wire. So I'm going to ask, are both ways valid to make all the bubbles are valid? for the choice of dA. Do you want your dA to be showing exactly inside the DL? Or do you think a dA that's bounded by the DL but has a really weird shape over here is also fine? So would the dA, the open surface bounded by your closed loop, here the metal wire, you make a balloon-shaped bubble. Is balloon-shaped surface, is that surface okay to do this, to do the Stokes theorem? Okay, all right, 10 more seconds. Let's think about and finish our vote in 10 more seconds. Okay, any last minute vote? Okay, I'm gonna close it. All right, so majority of you said, yes, we can choose a balloon-shaped surface or any weird surface there is, as long as it's bounded by the L. So, and why is that? How come we can choose such a surface? Or how do you convince the rest of us that it is, yes, it is A? What is the reason? Or maybe it doesn't have to be a well thought answer or any hunch, any thoughts that you had that supported your choice for A. Any thoughts? I will provide, go ahead, yeah.
I was thinking that, I mean, I might be wrong and I'm kind of second guessing myself now, but that the only thing that Stokes' theorem says is that it has to be some surface that's bounded by the line, the circle, and so it could be any surface. It doesn't matter as long as it has that caveat.
Yes, very good. Thank you, Benjamin. I was going to provide that argument myself as well, saying if it a particular surface, it would have specified already. But so far, we haven't heard anything about the choice of the surface. All it says is has to be bounded by the loop L. So any surface must work. Very good. It is indeed. Another thing you can try to think about is how make an analogy with Gauss's law. Remember in Gauss's law, we have E dot into dA is Q enclosed over epsilon naught. In Gauss's law, we don't have a particular choice of the surface. We can choose any weird surface as you want, and that will give us, as long as it's enclosing the same amount of charge, it's going to give us the same flux. Okay, calculating the flux might be difficult because E will be different at different points. If you choose a weird flux, weird surface is going to be hard to calculate, but the overall result is still going to be determined only by how many charges enclosed. So you can use that analogy to convince yourself here, it looks like no matter what surface we choose, this flux is essentially going to be all B dot into dl, no matter what flux you choose. So, okay, so going back to, let's not forget what we're trying to do. We're still trying to derive this equation, right? So let's use Stokes' theorem. Let's go into, so according to math, it says, if we're looking at the flux of the curl of B is equal to B dot into dl, okay? And we want to be able to derive this, and you can see we just simply need to plug in mu naught J. And curl of B is what? Is mu naught J, is mu naught J dot into dA. So previously we had said maybe the flux doesn't matter depending on the different choice of the surfaces. Does that mean that we do J dot dA and it doesn't really matter what surface you're going to choose? So here we have J dot into dA is going to be B dot into dl. We're really close to the last step. Okay, so now one more question. Here I'm giving you many different surfaces. They are all bounded by the same loop. The surfaces are indicated by the blue area. Okay, so if we were to compare the flux, or let me just call it the dot product between J and into dA, for these different surfaces, how would you rank them and how would you compare them? I'll give you a minute or two to discuss this, and we will come back for discussion. All right, let's go for 10 more seconds and then we can look at our answer. Okay, I'm gonna go ahead and close the vote, okay? All right, so I see the majority of you think that it's for D, it's all the same. For those who think they may not be the same, it looks like the one that looks the biggest mass, with the biggest area has the biggest flux. So how do we calculate the flux? Recall that this is a dot product, right? If this reduced to dA perpendicular, we had defined current is what? The integral of J dot into dA, which is J times dA perpendicular. So it doesn't really matter. You can dot into a large surface area. For example, you can have this kind of surface area, but it's really just a perpendicular one that matters. And they all have the same perpendicular area. So they're all going to be the same, which is they're all going to equal to current, right? They're all going to equal to the same current. But going back here, you can see that this is just going to be the current. So we have successfully derived the integral format of Ampere's law, which is mu B dot into dA is mu naught current. So when symmetry allows, we can use it to calculate a variety of problems. So including the current carrying wire, which was previously solved by Biot-Savart, and this was the result we got from the previous class, right? Now let's use Ampere's law to do this and see how easy and simple it can be. Okay, so just like Gauss's law, recall, before we can use Gauss's law, we have to convince ourselves that symmetry allows. So we need to be able to find a loop that B is everywhere a constant so that you can take B outside the integral, and also B is everywhere in the same direction as your DL to make your dot product easy to calculate. So in order to know what loop are we going to choose, let's say you want to find your B right here. So what kind of loop do we draw? We cannot answer that question is what loop to choose without answering the question, what is the direction of B and what is dependence of B? So here, let's say the current is in Z direction. So how can we convince ourselves the direction of B? So if you use cylindrical coordinates, there are only 3 different components. You either have a radial component, or you can have a Z component, or you can have a phi hat component. So here, I'm going to make a few claims to either choose one of these components or saying it cannot have this component. So my claim 1 is, I claim B cannot have S component, cannot be radial. Anybody would like to back me up on that claim? So I claim B cannot have an S hat component, which means B cannot be radially outward or inward. So, and why is that? Do I have any reasoning to claim to back up that claim?
Is the right-hand rule?
Yes, the right-hand rule is sort of a later as a product of that. So here we wanted to start from nothing, like we don't know anything. But later on we figure out, oh, it turned out it's this kind of dependence is described by a right-hand rule. But now let's pretend we don't have right-hand rule.
Well, B has to be perpendicular since del cross B is U naught J.
Ah, okay. So that can back up my second claim is B cannot have Z component because the Biot-Savart says B is in the same direction as DL cross R. So B is perpendicular to DL. When your DL is already in the Z hat, then B cannot be in the Z hat. So you have backed me up on this claim. What about the first claim? B cannot be radial. So if it were radially outward, it would be like this. This would be a radially outward B field. Is that problematic? Is that problematic? That looks like the E field, right? Radially outward from the center. Could that be a B field?
No.
And why not?
I think E and B are perpendicular.
And that's when we have a time dependent situation. Right now, we only have B. We don't have E in this case. So what will happen if everything is flowing outward? You must have a divergence, right? Here, indicating a positive divergence at the center. And that will violate, what would this violate? Divergence of B is equal to 0, right? So this will violate the no magnetic monopole law. So that's why B cannot be radially outward in this case. So which means only phi hat is the only possible situation. So my B is in the phi hat direction. So this is phi hat, which means if I were to choose a loop, I want to choose a sort of a circle in the phi hat direction because my B can only be in that direction. Okay, so I figure out that the direction of B is in the phi hat. Now I need to figure out the dependence of B. I also am going to make another claim that B cannot depend on Z. B cannot depend on Z because your source is a uniform and can extend infinity in Z. So B cannot depend on Z. So B in the phi direction, and also it cannot depend on Z, and must be depending on the S dependence. I also claim B cannot depend on phi because of the symmetry. If you look at phi all around, if I look at a B here versus here versus here, that shouldn't make any difference. Physically, you're looking at the same situation. So I argue B must be in this format. Then it's very easy to do the Ampere's law. So one more second and we're done. So we're going to choose a loop that is at a center S away from the center. So B dot into DL becomes B times 2 pi S, right? Is equal to mu naught I. So B is mu naught I over 2 pi S, and that's in the phi hat direction. Okay, so 2 pi S is the circumference of this loop. That just becomes B dl. So B dot into dl becomes B times dl and becomes B times 2 pi S. Okay, so we have found the same result using Ampere's law. So next class, we will continue to look at more examples solving using Ampere's law, including the current, the surface current. We're gonna redo that problem using Ampere's law, which will be much simpler. Okay, all right, that's all for today. I will see you guys, if not at office hours, I will see you on Friday's recitation. All right, have a good day, bye.
Thank you, Dr. Ryan. Have a nice day.
Thank you, bye-bye.